good to see you again, even if you can't see me. Enjoy the next part of the episode. And now that we have Eve walking, we can move on to the far more interesting and dangerous subject matter of speed.
Hold on, Victor. I also need to teach the children how to make their robots turn corners. How often do you have to turn in your day-to-day life?
I don't know, as I move basically all the time, I guess.
Precisely. So first, let us begin by learning how to turn our robot on the spot. Since Eve has 2 motors, he is capable of turning in one of 2 ways. A swing turn and a point turn. These 2 actions can be achieved with either one of 2 different action blocks, the tank block or the old familiar steering block. Each controls the 2 motors in different ways. Let us first observe the effects of the tank motor block.
Alright, as I move, I'll take care of this one. First, start up a new project. Let's call this one Swing Turn 1. Place the tank motor block next to the start block. As you will see, there are 2 power options, both set at 75. This is power to the left wheel, or motor B, and this is power to the right wheel, or motor C. Let us observe what happens if we set the left-hand one to 0 and then send the program to Eve to perform. You will see that he turns to the right, as only the right-hand set of wheels is receiving any power. The tank motor block allows us to control Eve's wheel motors separately, meaning that one wheel can spin, creating the turn effect, whilst the other wheel remains stationary. Much like when a tank turns, it uses only one set of caterpillar tracks, generating this swing effect as the moving caterpillar track runs a circle around the stationary one. If you swap the option settings around and set the left power option to 75 and the right power option to 0, then Eve will turn in the opposite direction, to the right. Simple as that.
Now let us create a point turn. A point turn is different from a swing turn as it uses both the B and C motors at the same time, so that your robot can turn on the spot.
So let's begin a new program for the new move. Let's call this one Point Turn 1. And, just like before, place a tank motor block next to your start point. Now, this time we want just as much power going to each set of motors so that they spin equally. But at the moment, both motors are identical, so are set to turn in the same direction, moving Eve forward. How do we make that wheel go the same distance in reverse? Switch to negative numbers, just like the speed setting on the steering block. So now, with the 2 motors running in opposite directions with the exact same speed, we should have a perfect turn on the spot, or point turn. Let's see it in action. These same 2 tricks can be achieved with a steering block, but the steering block, as its name suggests, is designed specifically for steering. I'll show you what I mean. So if you start a new program, call this one Steering Block 1, we'll add a steering block. Now, as you can see, this block has only one power option, and this option here marked 0 under an image of an arrow. This is the steering option. If you go to the steering option, you will see that it is controlled using this slider. The slider distributes speed between the 2 motors. If you move the slider to the left, power is decreased to motor B, and if you move the slider to the right, power is decreased to motor C. Now let's experiment with this. Try first setting the option to 50 and let us set rotations to 3, so we have plenty of movement to see the effects of the block. Now download and run your program. You will see that Eve performs a swing turn, so we know from this that this setting reduces the power to the right motor by 100%. Now let's see what happens when we increase the power option to 100 and then run the program. Now you can see that Eve performs a point turn, meaning 100% of the power is going to the right wheel, but in the opposite direction. So from this we know that 100 performs a perfect point turn, and 50 performs a swing turn, and the same is true for minus 50 and minus 100, but with Eve turning in the opposite direction as seen here. But anything between 0 to 50 will slowly decrease the power to the right motor, or motor C, and anything from 50 to 100 restores the power to that motor in reverse. And same goes for the negative numbers, but with the effects being on motor B, or the left motor. This is something you can experiment with in your own time.
But wait, Victor, this information is also important for when you want your robot to turn specific angles. You will often need your robot to turn 90-degree corners. We all do this in day-to-day life. As you may know, 90 degrees is a quarter of a circle. A full circle is 360 degrees, and a quarter of 360 is 90. Thus, Eve will achieve a 90-degree turn when he makes 1/4 of a full rotation.
So we want to find the best way of making Eve turn 90 degrees. Unfortunately, there is no one way of making it so that Eve will turn at a perfect right angle every time, as the distance between Eve's wheels will always be different depending on what shape he is built into, and this will affect the turning. But let's find the best way of doing this with the tracker robot. So first, we want to make it clear how far 90 degrees is. You can demonstrate this by using our old friend the ruler. Normally, for measuring angles, you will want a protractor. However, in this case, a ruler can do just as well since 90 degrees is a perfect right angle. We only need a new line which runs perfectly off of this first line. Simply line up the flat edge of your ruler with the first line and draw a new line going outwards. We now know that these lines are exactly 90 degrees apart, so we can line up Eve with our first line, and we want Eve, when he has finished his turn, to be lined up with the second line. The proper term for a line like this in mathematics is perpendicular. Now we can experiment with our program to achieve our 90-degree turn. In order to achieve our most accurate result, we should make this a point turn, so Eve will turn on the spot and remain on the corner of our perpendicular line. For this, let's use a tank motor block for accurate speed distribution between the two motors. So we know for a point turn we want to make one motor reverse at the same speed as the other. So let's set the second motor, or motor C, to minus 75. Now we need to find an amount of rotations to start our experiment with, since the number of rotations will control how far Eve turns. Well, 1 seems too boringly small a number, so let's start with 2 rotations. Once you have done this, you can test your sequence by connecting your computer to Eve's P-brick and downloading and running the program.
You will observe that Eve has turned further than 90 degrees. This means that we will need to make adjustments to our programming. In programming, this is known as debugging.
We know that if we increase the rotation option, then Eve will turn further, which is not the desired effect. If we instead decrease the option, we will get something closer to our desired effect. So, let us try the program again with the rotation option set to 1.5. Once you have done this, connect your computer to Eve's P-brick and download and run your program. Still a little too far. So this time we should take away less from our number of rotations, since we can see that we are pretty close to achieving our 90-degree turn. So I've got a good feeling about 1.39. Download and run your program.
We have achieved a 90-degree turn.
Congratulations! Someday you may even be able to determine the results of such experiments ahead of time using maths. But we'll come back to that later on. For now, there is your perfect 90-degree turn, a thing of beauty. Be aware that the surface you use for your Everstorm with these experiments can affect your results. If these numbers don't work for you, then you just need to get down to some debugging and work out the best number for your right angle. What's more, as with before, we can achieve the opposite effect, turning Eve in the opposite direction by swapping the speed control options. So we know setting motor B instead of motor C to -75 and setting motor C to +75 will tell Eve to turn 90 degrees in the opposite direction. And from here, you can also work out how to turn 180 degrees, or a half turn. Since we know that a quarter turn is 90 degrees and 180 is double 90, we simply must double the rotation option value to 2.76, as this is double 1.39. And there you have it, a half turn. Thank God. Does that mean that we can get on to the interesting bit now?
And now the moment everyone, but especially Victor, has been waiting for. Let's talk speed.
Woo! Let's do it!
Adjusting the speed at which your Everstorm travels is quite simple. When moving Eve forward, as we did earlier in the episode, you can simply adjust the motor speed from 100% to 50%, or any percent that you may desire. The top speed of your Everstorm robot depends on the size of the robot's wheels and the robot's shape, but is an average of 6 meters per minute. This too can be understood better using maths. Understanding speed to distance ratios is a very important experience for any young programmer.
Alright, fine! By understanding that Eve travels 6 meters or 600 centimeters in a minute, we can work out how long it will take Eve to travel any distance. For example, how long would it take Eve to travel 25 centimeters at top speed? First, we must work out how many times 25 goes into 600, Eve's top speed. The answer is 24. Now, we need to divide up the time it takes Eve to travel 6 meters, 1 minute, so it matches the smaller distance. We can do this by taking our new number, 24, and dividing the minute by that. This will leave us with the fraction of the time it takes Eve to travel 6 meters when he is traveling only 25 centimeters. So, 60 divided by 24 is exactly 2.5. We know from this that it will take Eve about 2.5 seconds to travel 25 centimeters. And this can be done with any distance. Say we wanted to work out how long it would take to travel 1 meter. It's the same principle. We know that 1 meter goes into 6 meters 6 times. So take that new number 6 and divide a minute by 6. That gives us 10 seconds. It all makes easy sense once it is understood. It is about changing the distance and time you are given by the same number to get our end result. The distance to time measurement is what is known as a ratio. In mathematics, this is kind of like a fraction. When you alter one part of a fraction, you must change the other in the same way. The same goes for ratios. If I have a distance of 60 centimeters, I have to divide 1/2 of my fraction by 10, and I have to do the same with the second half of the fraction, giving me 6 seconds. It can also be done in reverse. If Eve moves 600 centimeters in 60 seconds, how far will he move in 120 seconds? That's 60 times 2, so we times 600 by 2. 1,200 centimeters. Hopefully now this will make more sense. This type of mathematics is called speed to distance ratios. Here are some examples you can work out for yourselves at home. I think what he just taught us then was pretty cool. Plus, now we know how to make Eve move around, how to make him go faster or slower. He's one step closer to being able to do everything a person can do. I know, but I really wanted more speed. I mean, 6 meters per minute is cool and everything, but as I moved, managed to make it sound so boring there. Well, like you say, Eve's only a small robot, but would that be possible? To increase the speed? Well, in theory, yes. I mean, any motor can move faster if you increase the power supply, meaning that there is more power to move faster with. Well, how would you do that? You would need to either increase the voltage or the current, or both. Voltage refers to the amount of power that is available to an electrical device, like a motor. The current is the amount of power that is being allowed to travel from the power supply and into the electrical device. Think of it like water in a water pistol. The voltage is like the water inside the water pistol. The more there is, the greater the water pressure, so the faster it can be shot out of the gun. The current is like the hole in the front of the water pistol. The larger the hole, the more water can be shot through it at once. The problem, like you say, is that Eve's only a small robot and would need a larger battery in order to go faster. The more speed you use, the more power you lose. And also, if a robot weighs more, then it requires more power in order to move. A lighter robot will use less power. Make sure you're getting all of this down, kids. This is all really useful information for when you design a robot of your own someday. So, would it be possible to create a smaller battery that holds more power? In my time, yes, but not for you just yet. That's one for you kids at home to look into. What are you still doing here? Don't you have learning objectives to be covering? Go download our PDFs and we'll see you in the next section.